Your phone is smarter than you think, much smarter than most people realize. Every day, it filters spam, understands your voice, flags fraud, and optimizes GPS routes in real time. All of this is powered by machine learning. In this video, you will understand how machines learn, using one simple mental map and real examples from everyday apps. Why does machine learning matter today? Because we are generating more data than humans or traditional software can realistically handle. Every minute, massive volumes of messages, videos, signals, and payments flow through digital systems worldwide. As data grows exponentially, static programs cannot keep up. Machine learning adapts in real time to this massive flow. How fast is global data really growing? Faster than most people expect. All indicators show the same thing. Global data growth is not linear. It is exponential. In just a few years, what once felt massive now feels negligible. This explosive growth is exactly why new learning approaches are needed. So what is machine learning? Machine learning is about learning patterns from data to make predictions or decisions, without being explicitly programmed. There are three core ways machines learn from data. Supervised learning uses labeled examples, where the correct answers are provided. Unsupervised learning works without labels, discovering structure and patterns on its own. Reinforcement learning learns through interaction, improving through feedback and trial and error. Next, we will break down each approach using simple ideas and real-world examples. Let's start with supervised learning. The idea is simple. Models learn from examples with correct answers. It's like a student learning from corrected exercises. You give the model data along with the correct answers, called labels. The model learns the relationship between inputs and labels. Once trained, it can predict correct answers for new, unseen data. That's how apps detect spam, estimate house prices, or recommend content. In supervised learning, models solve two types of prediction problems: categories or numbers. The first type is classification. Here, the model predicts a category or a class. For example, is this email spam or not? Is this image a cat or a dog? The output of a classification model is a label, like yes or no, or one class among many. The second type is regression. Here, the model predicts a number. For example, what will this house sell for? Or what will the temperature be tomorrow? The output of a regression model is a value, like a price, a quantity, or a measurement. There are many ways to solve classification and regression problems, and no single model works best for every case. The first family is classic models. This includes linear regression, logistic regression, and decision trees. These models are simple, fast, and interpretable. They are a great choice when you need clarity and quick results. The second family is ensemble models. Examples include random forests, XGBoost, and LightGBM. They combine many models together, and often deliver strong performance on tabular data with minimal tuning. The third family is neural models. These include multi-layer perceptrons, convolutional networks, and recurrent models. Neural models shine on complex data, like images, text, audio, or very large datasets. The fourth family includes probabilistic and distance-based models, like naive Bayes and k-nearest neighbors. They are often chosen for their simplicity and speed, especially when data is limited. Let's look at a real example of supervised learning. How your phone detects spam emails. This is a classic classification problem. Each email is either spam or not spam. First, the model looks at the input, the email content, the sender, and other metadata. During training, each email comes with a label, spam or not spam. These are the correct answers. The model learns patterns from thousands or millions of labeled emails. Once trained, the model can instantly classify new emails it has never seen before. Spam and threats are blocked before you even open your inbox. You use this every day. Let's look at another real example of supervised learning: predicting house prices. This time, the task is regression. The goal is to predict a number, not a category. First, the model looks at the input features, things like size and location. During training, each house comes with a known selling price. This is the label the model learns from. The model learns the relationship between these features and the final price. Once trained, the model can estimate the price of a new house it has never seen before. This helps buyers, sellers, and real estate platforms set fair prices and make better decisions. So far, the data always came with answers. Next, unsupervised learning. Let's move to the second major approach in machine learning, unsupervised learning. The idea is simple. The model explores data without being given the correct answers. It's like a child sorting toys by shape or color, without anyone explaining the rules. You give the model only raw data, no labels. The model discovers patterns and structure on its own, grouping similar items or spotting unusual cases. This helps apps organize photos, group customers, or detect unusual behavior. Unsupervised learning is about discovering structure in data, not following examples. Unsupervised learning focuses on two main tasks, all without labeled examples. The first task is clustering. The goal is to discover natural groups inside the data. The model groups similar items together based on patterns it detects automatically. For example, clustering can segment customers, group similar images, or detect unusual behavior. The second task is dimensionality reduction. This is about simplifying complex data. The model compresses the data, keeping the most important information and removing noise. This makes large datasets easier to visualize, analyze, and work with. Let's look at a real example of unsupervised learning. How Netflix knows what you might like. This system works without labels. Netflix is not told in advance what type of viewer you are. Instead, Netflix observes your viewing behavior, what you watch, rewatch, skip, or stop early. The model groups viewers with similar habits together. This is clustering. Once you are in a cluster, Netflix recommends shows that people in your group tend to enjoy. That's why recommendations often feel surprisingly accurate, even without asking you to rate anything. Quick pause. If this is helping you make sense of machine learning, like or subscribe to support similar content. Let's look at another real example of unsupervised learning. Dimensionality reduction. Imagine a dataset with too many features to visualize directly. Dimensionality reduction shrinks all that information into just 2 or 3 dimensions. This lets you clearly see the main patterns, like points forming groups on a simple chart. The model keeps the most important information while removing redundancy and noise. The result is faster models and insights that are much easier to see and explore. Next up, we'll see models that learn by acting. Reinforcement learning. The third major approach in machine learning is reinforcement learning. The idea is simple. The system learns by acting, not by looking at correct answers. It's like learning to play a game by practicing, not by reading the solution. The system interacts with an environment and decides which action to take next. Each action leads to feedback, a reward if things go well, or a penalty if they don't. Over time, it learns which actions lead to the best long-term results. This approach helps systems decide when to brake or accelerate, or which move to play. Reinforcement learning is about learning through interaction and feedback, not through examples. In practice, reinforcement learning problems fall into 2 main categories. The first category is control. The system decides how to act in a given situation. For example, which move to play in a game, or how a robot should move. The output is simple: the next best action. The second category is sequential decision-making. The system learns a strategy over time. This includes playing an entire game, managing traffic lights, or optimizing long-term performance. Instead of a single action, the output is a policy, a strategy that maximizes long-term rewards. Most real-world reinforcement learning systems fit into one of these 2 categories. Let's look at a concrete example of reinforcement learning through a game-playing AI. Imagine an AI playing a game for the very first time, with no instructions and no strategy. The AI is the player, and the game itself is the environment. Every action changes what happens next. At each step, the AI takes an action and receives feedback, a reward or a penalty. By repeating this process thousands of times, it learns which actions work best. You've now seen supervised, unsupervised, and reinforcement learning. Next, let's compare them side by side. Let's bring everything together by comparing the 3 main machine learning approaches. Supervised learning learns from correct answers. It is trained with labeled examples. Its main question is simple: what is the correct answer for this input? The output is a prediction, like detecting spam, predicting prices, or recognizing images. Unsupervised learning works with raw data, without labels or correct answers. Its key question is, what is going on in this data? The output is structure, like clusters, groups, or hidden patterns. Reinforcement learning learns through rewards and penalties. Its main question is, what should I do next to get the best long-term result? The output is an action, used in games, robots, or self-driving systems. Machine learning has several key strengths that explain why it is so widely used today. First, machine learning learns complex patterns that fixed rules cannot capture. Second, it handles massive volumes of data efficiently, far beyond what humans can process manually. Another major strength is that performance improves with more data. The system improves with experience. Machine learning can also generalize. It applies what it learned to new, unseen situations, not just past data. Finally, machine learning automates tasks by making predictions or decisions, reducing human effort. These strengths make machine learning powerful, but it is not magic. Next, let's look at its limitations. Machine learning is powerful, but it also has important limitations to keep in mind. First, most machine learning models need large amounts of data to learn reliably and perform well. If the data is biased or unbalanced, the model will learn those biases and can produce unfair results. Accuracy alone can be misleading. Models must be evaluated using the right metrics for the real-world task. Training large models can be expensive, requiring significant time, computing power, and energy. Even when they perform well, models do not truly understand meaning or intent. To finish, let's summarize the most important takeaways about machine learning. First, machine learning learns from data. It discovers patterns to improve predictions and decisions. There are three main approaches: supervised, unsupervised, and reinforcement learning. That's why machine learning uses different tools for different tasks, such as classification, regression, clustering, or control. There is no one-size-fits-all model. The best choice depends on the data, the task, and the constraints you face. Machine learning is powerful, but not perfect. It can be biased, costly to train, and it doesn't truly understand context. Thanks for watching. If this video helped you, feel free to like, comment, or subscribe.